in our 2-unit series system, where the two elements are loaded by the same load P, and the failure probability is P of R1 less than P union R2 less than P, so it's a union probability. What happens if P is random? So if P is random, then we could interpret the PF that you see above, P R1 less than P and R1 less than P or R2 less than P, as a conditional probability. So P of F sys given Q, the random load, has taken on an arbitrary value of P, non-random. That is what we have already seen, what we already discussed at length in the previous slide. So we have done this sort of thing quite extensively in the last few lectures. So we invoke the theorem of total probability and get the unconditional F sys probability of system failure, as the integration of the kernel, which we already had with respect to the PDF of Q, the random load. So this could be computed without any problem using Monte Carlo simulations, and we have been doing this, so it should not be difficult now. But let's walk through an example and see what sort of effect this introduction of the third random variable, randomness in the load, would cause. Obviously, we should expect that the failure probability should go up because now load is also uncertain. Let's see how that looks like through an example, and we'll continue with the example we were discussing in the previous slide. So R1 and R2 are joint normal with the correlation coefficient, and we will fix the correlation coefficient at 0.5. It's a reasonable number, that's all, and the means and the standard deviations are the same as before, the means being 10 and the standard deviations being 2, as we had in the previous slide. Q, we now we say it's a random variable. Let's pick the Gumbel distribution for Q. Let's say its mean is 6, so it's one of the 4 cases that we looked at in the previous slide, and it's that curve on which we made that green oval, which I wanted us to remember. So the mean is set at 6 units, and the coefficient variation is rather large, 30%. So that is our Q. Now it's most straightforward to write a small program and do this, and let's see how the code would look like in such a situation. So I present the main lines of that code. So I first define all the properties, the means and the standard deviations for both the random variables, and in fact I want to go through this in little detail, in some detail, because we need to know how to write the syntax for Matlab when we are discussing when we are going to call the bivariate normal CDF. So we need to define the mean vector, which is what you see, mu being m1 and m2 in a row vector. The correlation coefficient rho is 0.5, and now we have to define a 2 by 2, a square covariance matrix. So that's what we do in the second line of the code. I have put the rows next to each other. It's not necessary. I just wanted to save some space and fit everything in one slide. So the covariance matrix for R1 and R2, the first diagonal element is sigma 1 squared, so that's what you see as d1 to the power 2. Then the off diagonal term is the covariance term, which is rho sigma 1, sigma 2, and then we come to the next line after the semicolon, that is again rho sigma 1, sigma 2, and the final term, the second diagonal element, is sigma 2 squared. So for any larger problem, and if it's jointly normal, we need to carefully define the covariance matrix, because that's what Matlab needs. Then we come to the Gumbel random variable. Its mean is 6, its COV is 0.3. So if I have done it correctly, we have the SD, the standard deviation of P, the alpha of the Gumbel distribution, and the U of the Gumbel distribution also in terms of the mean and alpha. So assuming that all that coding is correct, I can now start the Monte Carlo simulation. So you see 1000 here, but actually I have done about 100 times more, and the answer that you will see corresponds to about 100,000 simulations. So the next is we enter the Monte Carlo loop, initialize the sum, because after all we are computing an expectation, as you see on the integral above. PF6 is integral of the union probability multiplied integrated with respect to FQ P dP. So it's that expectation we are computing. So we generate P every time because the expectation is with respect to P. So the line, the first line inside the Monte Carlo loop generates a value of the Gumbel load P, and then because each of these random variables R1 and R2 is loaded equally, that's why the load vector, which is again something that will be required by the Matlab bivariate normal CDF function call, that would require the load vector, or the vector at which I evaluate the bivariate normal. So that is P and P. So it comes from the mechanics of the problem. If there was any other value of the individual member loads, that's what we would put. Now we are ready to call the normal CDF functions. So we go the same way as we did before. PF is PA plus PB minus PAB, or P R1 less than P plus R2 less than P minus P R1 less than P and R2 less than P. So that's what we are doing. The first term is the one-dimensional normal integral. The second term is the one-dimensional normal integral, both evaluated at P. And the third term, the subtracted term, is the bivariate normal CDF. So it's important we learn this syntax because we're going to use this for larger problems as well. So it's MV and CDF evaluated at the load vector, where mu is the mean vector and COV R1 R2 is the covariance matrix of the bivariate distribution. And once we are done with that, we keep adding that estimated PF sys to the sum, and then when we are out of the loop, then we take the average, and that's all there is to it. As this is what I wanted us to remember, that when Q is exactly 6, the mean value, no uncertainty, so PF sys was 0.04 approximately, and with this, after about 100,000 simulations, the answer is the expectation that we computed is about 0.11. So there is a substantial difference which should be expected, but this tells us that we have the ability to include any sort of randomness, provided we understand the mechanics of the problem and provided we are able to include dependence where it should be, and then go through systematically and get the final answer.